Hello and welcome back to the course on Introduction to Solid State Physics. In the last lecture we have seen the dynamics of the electrons which can be obtained from the band structure. The slope of the EK diagram corresponds to the velocity of the wave packet associated with the moving electron, whereas the curvature of the EK diagram is related with the effective mass of the charge carriers. In today's lecture, let us try to see how the conduction can be explained using the band diagram. So let us consider different types of bands in a solid. This is in the fast Brillouin zone. In the reduced zone scheme, this is the E versus K diagram, and suppose let us start with absolute zero temperature. Here we are having the filled circles are filled bands, whereas the empty circles are empty bands. Filled band means it contains the charge carriers, that is the electrons. Empty band means it doesn't contain any kind of charge carrier, and in between them we are having the existence of forbidden band. Between this and this we are having the existence of forbidden band. So these yellow portions are allowed bands. So here these are the electronic states. It is completely filled. Here also it is completely filled, whereas these bands are completely empty at T equal to 0 Kelvin. Let us name these bands as band 1, band 2 and band. This is band 1, 2, 3, 4, like this. Band 1 and 2 are filled bands and they are allowed bands, and between them we are having the forbidden region. This is again the forbidden region, this is again the forbidden region. Band 3 and band 4 are allowed bands, but they are not occupied by any charge carriers. You can see here the states are available, they are the allowed states, but they are not filled with the electrons. So now the picture is clear. There are 4 bands. Out of these 2 bands are allowed and they are completely filled, and the upper 2 bands, that is 3 and 4, are allowed bands but they are completely empty, and in between all the bands we are having the existence of forbidden region, at which there are no electronic states available to be occupied. So for first, now let us try to explain the conduction for these 4 bands. To start with, let us look at the band 3 and band 4. At the band 3 and band 4 there are no charge carriers. So it is obvious that they cannot conduct electricity. In one dimension, if you consider, the electrical current can be represented as minus of Q, the length of the solid, summation over all the electrons, all the electronic states, VI. So this represents the electronic current, and since Q is equal to 0 for band 3 and band 4, because there are no electrons here, so Q or V both are going to be 0. It doesn't have any significance. That's why bands 3 and band 4 are not responsible for any kind of electrical conduction. So the empty bands do not conduct electricity. Now come to the bands 1 and 2. Bands 1 and 2 are completely filled. That means there are no free electronic states where the electron can undergo transition. Suppose we are applying one electric field E, and we know that the force experienced will be the charge times E, and this force has to be equal to H cross dk by dt. If you recall, the rate of change of crystal momentum is equal to the external force experienced by the electron, and in fact this can be written as H cross k at certain time tau minus k 0 at time t equal to 0. That means the electron is going from one k state to other k state due to the application of the electric field. But since there are no empty states available for the electron to go, that's why this kind of transition is not possible. So let me erase the ink here. So k tau minus k0 is equal to E by H cross, but this transition is not possible because there are no free k state, there are no empty k state at which the electron can undergo transition. For the conduction to take place, the k state or the electronic state must change upon the application of the electric field. But since there are no vacant states available, it is not possible for the electron to go from one k state to the other k state. Because of this reason, completely filled bands cannot conduct electricity. So fully or completely filled bands cannot conduct electricity. At T equal to 0 Kelvin, two concepts we got it. Empty bands cannot conduct electricity, and completely filled bands also cannot conduct electricity. Since all the k states are filled, the electron cannot move under the application of the electric field, and hence no conduction is possible. We are having two concepts clear here. Completely empty band and completely filled bands cannot conduct electricity. Now let us try to apply some temperature at any finite temperature. We'll see what is the situation. Suppose at room temperature, that is 300 Kelvin, what is the status? Let us examine. When we increase the temperature, few electrons from the band 2 undergo transition due to the thermal energy, and they are occupied in the band 3, and the number of electrons are very less. So by this process, what is happening here? The band 2 is almost filled, it is nearly filled, except very few states at the band H. Similarly, the band 3 also is completely empty, nearly completely empty, except few states which are occupied. Whereas the band 1 and band 4, the situation remain the same. Band 1 is already fully filled, no empty states are available, whereas the band 4 is completely unoccupied. Therefore, by applying the thermal energy, at room temperature, we are able to have a very nearly filled band and a very nearly empty band, but it is not completely filled, neither it is completely empty. There are few unoccupied states are there, even though the number is very less, but it is definitely not completely filled. With this, let us try to examine the conduction in the solid. Let us examine the bands, band 1 and band 4 first, then we will come to band 2 and band 3. Under the application of the electric field, what will happen? This band 1 is already it is filled, so no effect on this. Due to band 1, no conduction can take place. So band 1 is not responsible for any kind of conduction. Similarly, band 4 also no conduction. No conduction. Now let us see what is the situation for band 2 and band 3. For that, let us rewrite the expression for the current. We have defined the current to be equal to minus of Q by L, assuming a one dimensional solid, summation over all the states of VI. So band 3, let me go to band 3 once again. Band 3 contains very few states are there which are occupied. So you have to take the summation of these filled states, then we can get the current flowing due to band 3. So the current due to band 3 will be equal to minus of Q by L, sum over all the filled states, and this number is very less, very few states are occupied. So sum over the velocity of very few states which are occupied. On the other hand, for band 2, the same situation, the same equation can be written like this. The current due to band 2 will be equal to minus of Q by L, sum over all the field states, sum over the velocity corresponding to all the field states. But this number is very large, so practically it is impossible to sum over this many large number of electronic states. If we go back to our earlier lecture, we know that the number of electronic states or the number of k states in the first Brillouin zone is equal to the number of primitive cells, and which is nearly equal to the number of atoms, and is the number of atoms inside the solid, which is roughly of the order of around 10 to the power 22 per centimeter cube. So here you have to take the sum over all these 10 to the power 22 states, which is practically not feasible. So you have to find out one alternative way to take into account this summation. For that, let us look at the symmetry of the band structure. So if you look at the symmetry here, so either this band or this band, we can see that it is symmetric around k equal to 0. The slope is symmetric around k equal to 0, but here the slope is negative and here the slope is positive. Similarly here the slope is negative sorry, here it is positive and here it is negative. Due to the symmetric nature of the band diagram, around k equal to 0, the net velocity must be equal to 0. Due to all the states, the net velocity must be equal to 0. We can write it mathematically in this manner. And before that, we know the expression for the velocity. It is related with the slope of E versus K diagram, that is 1 by h cross delta E by delta K. Since the velocity is symmetric about k equal to 0 and is in opposite direction, when you take the sum over all the states, the net velocity must be equal to 0. Since it is symmetric but they are having opposite direction, as we discussed here. Once again, let us go to the diagram to have a better understanding. Since the slope is negative here, the velocity will be negative. That means it will be in the opposite direction than that of this one. Because of this, the net velocity must be equal to 0 due to all the states. And this we can split into the filled states and empty states. This can be split into filled states and empty states. So let us write that. So sum over all the filled states velocity plus sum over all the empty states velocity will be equal to 0. Or in other words, sum over all the filled states velocity will be equal to negative of the sum over all the empty states. Or this empty states we can write here sum over all the filled VI is equal to minus of sum over all the empty VI. But in the empty states there are no electrons, so this negative velocity can be associated with some kind of hypothetical particles, and later on we will call these hypothetical particles as the holes. The holes are traveling with some negative velocity because they are associated with the empty states, and these hypothetical particles are called as the holes. Now let us rewrite the current due to band 2. So this was the expression. So instead of summing it over all the filled states, now we are going to take the sum over all the empty states. Because of this negative sign, now you have to write it as plus q by L. Earlier it was minus q by L, and since because of this relation we have to put a positive sign here, so we can think that the current is due to an hypothetical particle having charge q, having charge plus q. It is not because of the electrons but because of some positively charged particles, hypothetical particles having the charge plus q, and these particles are indeed called as the holes, which are hypothetical imaginary particles. So what is the advantage we are going to do by this? Here we are going to sum it over around 10 to the power 22 atoms, whereas this number is very small. This number is related with the thermal energy. So very few electrons will go from the valence band or the band having lower energy to the higher energy. So this summation will be pretty simple rather than summing it over 10 to the power 22 number of electrons. And we can rewrite this current as plus q by L sum over all the empty states in the band 2 the corresponding velocity. So we have introduced one new kind of hypothetical particles which are having a mass, which are having a charge which is plus E, and the effective mass is going to be negative. Because if you look at the band diagram here for band 2, let me erase the inks here for more clarity. So if you look at this band diagram here, this band 2, so here the slope is negative, sorry, the curvature is negative. Because of that, we are going to see one hypothetical particle having positive charge and a negative curvature. A negative curvature means it is having a negative effective mass. If you recall, we have written that the effective mass is written as h cross square by delta square E by delta k square. So it is related with the curvature of the EK diagram, and since the curvature is negative, that is why the mass will also be negative. And this new particle having a positive charge and negative effective mass is called as the holes. And these holes are responsible for the conduction in the insulators and semiconductors. With this small idea, we can distinguish between the metals, insulators and semiconductors. So in case of metals, we are having partially filled bands, because we know the completely filled bands cannot conduct electricity, the completely empty bands cannot conduct electricity, but we know metals are highly conducting, they are electrically good conductors. So we need to have many number of empty states and many number of carriers. So the carriers can easily change their k state when we apply an electric field. So if you are having a band which is partially filled, then easily the electron can undergo the transition from one k state to the other k state upon the application of the electric field. So metals are having partially filled bands, whereas in case of insulators and semiconductors, we are having either fully filled bands or fully empty bands, so that due to thermal energy, few carriers can be excited, to the next empty band, and if the energy difference between them is of the order of around 1 to 2 electron volt, we generally call it as the semiconductors, because it is very easy for the charge carriers to go from the lower band to the higher band by the application of thermal energy. If it is very difficult, then we call it as the insulators. As such, there is no hard and fast difference between the semiconductors and insulators, because they are relative terms which can be changed at which temperature regime you are discussing the particular sample. the sample is exposed to what kind of temperature. Based on that we can distinguish between the insulators and semiconductors. But the basic difference between the metals and insulators is that metals are having partially filled bands, whereas semiconductors are having completely filled band or completely empty band. So that at room temperature few carriers can go from the one of the lower band to one of the higher bands, which was earlier completely empty. And usually the lower band is called as the valence band, and so if this is the EK diagram, so this is the completely empty band, this is the completely filled band, and this lower band is called as the valence band, and the upper band is called as the conduction band. And the energy difference between the valence band maximum VBM and the conduction band minimum CBM is what is called as the band gap. If the band gap is small enough, then we call it as the semiconductors. If the band gap is very high, we call it as the insulators. But again, the distinction is not very clear. It all depends at which temperature regime you are discussing the sample. If it is having enough energy, then the electrons can easily go from valence band to conduction band. That category of samples are called as the semiconductors. If it is difficult for the electrons to go from the valence band to the conduction band, then it is called as an insulator. So with this we got a clear-cut idea between the how to distinguish between the metals and semiconductors. So metals are partially, they are having the partially filled bands, so that the electron can undergo transition from one K state to the other K state, whereas in case of insulators or semiconductors we are having either completely filled band or completely empty band, so that by the application of any external energy such as thermal or optical energy, few electrons can go from the valence band to the conduction band, so that conduction can take place. But the conduction is poor compared to that of the metals. So next lecture we will be discussing about the conduction in case of a semiconductor. Thank you.